The truth is out there, and so is the future. Welcome to GenAI Cafe, where we explore the strange, the powerful, and the unexplained world of generative AI. With your host Nico Peters, and in each episode, we'll uncover how artificial intelligence is reshaping our reality, pushing the boundaries of creativity, and challenging everything we know. Are we witnessing the dawn of a new era, or playing with forces we can't control? Stay tuned and prepare yourself to venture beyond the edge of innovation, where technology meets the unknown.
Artificial intelligence (AI) has become an integral part of modern life, revolutionizing various sectors such as healthcare, finance, and transportation. Its applications promise to solve complex problems and improve efficiency and productivity for businesses and individuals alike. However, with these advancements comes a crucial aspect that we must not overlook: its environmental impact. As AI systems grow more sophisticated and pervasive, so do their energy demands and the data required to train and operate them. Every time we train a machine learning model, especially larger models, significant computational resources are consumed, which in turn rely heavily on electricity, a resource that can have a substantial carbon footprint depending on its source. Furthermore, maintaining and cooling data centers, which store vast amounts of information necessary for AI training, also contributes to environmental strain by consuming electricity and water resources. Therefore, it is imperative that we pay attention to these environmental costs as we push further into the AI frontier. Understanding the full lifecycle impact of AI technologies allows developers, policymakers, and end users alike to make informed decisions about their AI usage, striving towards innovations that not only excel in performance but also in sustainability. In our next section, let's delve deeper into the specifics, examining why AI requires significant amounts of energy and data, highlighting the importance of energy-efficient practices in AI development. AI systems have made remarkable strides in various domains, yet beneath the glossy surface of innovation lurks a considerable burden of energy and data consumption. As we delve into the environmental cost of AI, let's examine the fundamental reasons why these systems demand substantial resources. First, to understand energy demands, consider the computational intensity of AI processes. Machine learning algorithms, the backbone of AI, undergo immense computational workloads, translating to enormous energy consumption. These workloads arise not only from executing complex mathematical operations, but also from the data retrieval hardware cycles required in these tasks. Secondly, AI models derive their effectiveness from vast data sets. Training these models involves processing and storing gigabytes to petabytes of data. This data serves as the learning material AI systems depend on to understand variables, make predictions, and identify patterns. Data retrieval and storage. Gathering large volumes of data requires extensive storage solutions and data centers that, in turn, consume significant energy. Data processing. Operating on such extensive data sets requires numerous iterations of processing, which leads to increased electrical demands. Additionally, the more sophisticated an AI model becomes, the larger its footprint. This complexity ensures high accuracy and improved performance, but also significantly spikes energy and data requirements. AI models are continuously evolving, necessitating the ongoing collection and processing of fresh data to maintain their relevance and accuracy in a rapidly changing world. Understanding these demands sheds light on the trade-offs between advancing its environmental repercussions. As we advance to the next section, we'll delve even deeper into particular aspects of AI that amplify these environmental concerns, focusing on the training of large AI models. Training large AI models is an intricate process that involves several stages, each contributing to environmental footprint. Let's delve into these stages to understand their implications better. Firstly, data collection and pre-processing involves curating vast amounts of raw data from diverse sources. This step is crucial. Quality and diversity of the data directly impact the performance of the AI model. However, sourcing and cleaning such vast datasets requires significant computational resources, contributing energy consumption. Next, let's talk about model selection and tuning. During this phase, various algorithms are tested to find the optimal one for the task. This process is computationally expensive, involving numerous trials and errors, which translates into prolonged use of energy-intensive hardware. Training is the most resource-demanding step. It involves running data through the model multiple times to adjust weights and biases, a process that can take from days to months depending on the model's complexity. Supercomputers and powerful GPUs often run at full capacity, consuming large amounts of electricity and generating heat, which further demands cooling systems. Additionally, there is hyperparameter optimization, which navigates the search space of model parameters to enhance performance. This not only adds to computational demands, but also lengthens the training duration, increasing resource usage. Finally, validation and testing ensure the model's accuracy and efficiency. While less taxing than other stages, this step still requires considerable computational power to handle multiple iterations for fine-tuning. The cumulative effect of these processes is a substantial environmental cost, primarily due to the intense energy demands of running high-performance hardware. Recognizing this impact is crucial in developing more sustainable AI practices. As we continue to unravel the environmental implications of artificial intelligence, another critical aspect that demands our attention is the tremendous scale of energy consumption involved in AI research and development. The burgeoning field of AI development isn't just intellectually challenging, but also energy intensive on a massive scale. AI systems, especially those powered by deep learning and neural networks, require substantial computational power. This power translates to a significant appetite for electricity. With the training of large AI models requiring weeks or even months of processing on hundreds of powerful GPUs, the energy consumption becomes astonishingly high. This immense demand for energy not only accelerates the depletion of natural resources, but also impacts our environment negatively by contributing to carbon emissions. It's essential to consider that the majority of electricity worldwide is still generated from fossil fuels, which means the carbon footprint of AI research is substantial. To put it in perspective, a single AI model training can emit over 280,000 kilograms of CO2, equivalent to the lifetime emissions of 5 cars. Such statistics are a chilling reminder of the environmental cost tied to advancements in AI. The challenge, therefore, lies in striking a balance between the growth of AI technologies and sustainable practices. As we navigate this journey, it becomes imperative to explore solutions that reduce energy consumption and lower carbon output. Establishing energy-efficient methods and harnessing renewable energy sources can play a pivotal role. Furthermore, collaborative efforts among AI developers, policymakers, and environmentalists can significantly mitigate the ecological impact. Understanding these issues sets the stage for our discussion on the infrastructures supporting this AI evolution, particularly data centers, their energy consumption patterns, and how they contribute to the overall environmental ecosystem. Let's delve into that next. Our reliance on artificial intelligence requires robust data centers that house the heart and brains of AI operations. As much as these hubs have spurred technological advancements, they also pose significant environmental challenges. To comprehend the full scope of this issue, it's essential to dissect how data centers function and significantly to environmental stress. Data centers are massive facilities filled with racks of high-powered servers operating 24/7 to process, store, and analyze an incredible amount of information. The AI models, algorithms, and data sets they handle demand immense computational power, setting off a cascade of energy consumption. Several factors contribute to the environmental impact of data centers. Energy use. The primary source of their environmental footprint is the sheer volume of electricity needed to keep operations steady. This extends to both running servers and maintaining optimal cooling systems, which ensure continuous performance. Water consumption. Many data centers use water-based cooling technologies, adding to local water scarcity concerns. Land usage. Constructing and maintaining data centers involve a substantial amount, often at the cost of disrupting local ecosystems. The exponential demand for AI capabilities necessitates more data centers, which in turn exacerbate these environmental stresses. This connection between AI and environmental cost calls for a coherent strategy focusing on sustainability. Various companies are exploring innovations aimed at reducing the environmental toll of data centers. These include renewable energy commitments, improvements in energy efficiency, and more sustainable cooling systems. However, these advancements must be scaled more broadly to counterbalance the burgeoning energy demand. As the backbone supporting AI, data centers play a pivotal role. Deciphering their environmental impact provides valuable insights into the broader ecocentric discourse surrounding AI. Moving forward, integrating sustainable practices in these centers is not just an option, but a necessity to curb the rising tide of ecological stress. Building on our understanding of data centers' roles, it's crucial to dive into the carbon footprint activities. As carbon emissions are a pressing concern that often flies under the radar but has significant environmental implications. Its carbon footprint is substantial when you consider the computational power required to train and maintain large models. These processes often run for days or weeks, consuming immense amounts of electricity. This energy consumption translates to greenhouse gas emissions, with a notable portion attributed to fossil fuel-powered grids. Consider this. Training a single AI model can emit as much carbon as 5 cars over their entire lifespans. This stark comparison underscores the need to evaluate AI's impact on our planet consciously. Let's put AI's carbon emissions into perspective by comparing them to other industries. While technology and digital services make up a modest percentage of global emissions, AI has the potential to accelerate this footprint. For example, while industries like aviation and shipping are well known for their carbon contributions, the rapid growth of AI could soon rival those sectors if unchecked. However, it's important to recognize that AI also offers opportunities for reducing carbon emissions in other areas, such as optimizing energy use in buildings or improving the efficiency of supply chains. Balancing the scales between AI's carbon output and its environmental benefits is key. As we continue, we'll explore specific scenarios illustrating AI's environmental cost and delve into innovative paths forward. Understanding both the challenges and the potential of AI's impact is imperative for steering the future towards sustainability. Now that we've explored the carbon footprint of AI technologies, let's delve into some concrete examples to understand their environmental impact further. Examining case studies sheds light on the tangible and often under-discussed consequences of AI projects, offering insights that spur innovation while keeping sustainability in mind. One prominent example is the massive data centers required for AI applications. Take the case of Google's data center in the Dalles. It's a prime example of scale where AI operations demand enormous computing power, effectively leading to substantial energy consumption. Despite measures like artificial cooling, the energy draw is significant, often outstripping smaller cities. Another illustrative case is OpenAI's GPT-TT model. This highly complex language model necessitated vast computational resources during its training phase. Running at a scale of billions of parameters, GPT-3 exhibited considerable energy demand, equating to the energy used by several hundred homes for a year. Such undertakings highlight AI's dependency on large computational frameworks, raising crucial questions about their sustainability. And there's AI's role in digital targeting. Analysis by Meet reviewed that personalized and served online consumes a small yet noticeable amount of electricity, multiplying across billions of requests daily. This demonstrates how omnipresent AI applications contribute significantly to environmental concerns over time. Moreover, AI systems used in autonomous vehicles provide another case study. Tesla's AI-powered autopilot, law heralded for potential safety and efficiency, requires ongoing data processing and transfer. This relentless need for data streams and computational power creates a concealed environmental burden. These case studies highlight the dual nature of AI. While presenting transformative opportunities, they also pose significant environmental challenges. Up next, we will look into companies that are spearheading efforts toward more sustainable AI, offering a beacon of hope and direction for the future of technology. Let's take a closer look at companies that are pioneering the route towards sustainable AI. These organizations are investing in innovative practices and technologies that aim to reduce the environmental impact of artificial intelligence. Google. Google has long been a frontrunner in sustainable technology efforts. Their AI systems are powered by 100 renewable energy, and they have implemented machine learning algorithms to optimize data center energy efficiency, resulting in a 30% reduction in energy usage. Microsoft. Microsoft is making headway with its AI for Earth program, which supports projects stemming from research on using AI to tackle global environmental challenges. Furthermore, Microsoft has committed to becoming carbon negative by 2030, with AI playing a vital role in its sustainability roadmap. IBM is tackling the sustainability challenge by developing AI systems that are inherently efficient. The company's Green Horizons initiative uses AI to predict and improve air quality in cities worldwide, demonstrating how AI can directly address environmental issues. NVIDIA, as a leading provider of AI hardware, NVIDIA focuses on developing more energy-efficient GPS. By incorporating sustainability into the design and manufacturing processes, NVIDIA enables more sustainable AI training in inference operations. OpenAI is actively researching ways to minimize the footprint of large AI models without compromising performance. They have made shifts towards minimizing data center power consumption and optimizing their algorithms for better energy efficiencies. These companies are not only reducing their carbon footprints, but also setting industry standard. Their efforts illustrate the possibilities when sustainability becomes an integral part of AI development. As we recognize these leaders, our exploration into improving AI's efficiency continues. As we pivot our focus towards the innovations in AI efficiency, it's important to highlight the groundbreaking technological advancements that aim to minimize energy consumption in AI systems. These innovations are pivotal in ensuring that AI doesn't just become smarter, but also more environmentally conscious. Let's delve into a few key technologies driving this transformation. Model optimization techniques. The development of more efficient algorithms and neural network structures is crucial. Techniques such as pruning and quantization are enabling networks to require fewer computational resources, significantly cutting down energy usage. Edge computing. By processing data closer to the source, edge computing reduces the necessity for instant communication with centralized data centers, which in turn lessens the energy demands typically associated with cloud-based AI systems. Energy-efficient hardware. New hardware like specialized AI chips and GPUs are being designed to perform complex calculations with minimal energy. These components are optimized for getting maximum performance per watt, thus ensuring high efficiency. AI-powered energy management. Interestingly, AI itself is being utilized to enhance its own sustainability. Technologies that anticipate and adapt to fluctuating energy demands can optimize power usage in real time, ensuring that energy is only utilized when and where it's necessary. These innovations are not just theoretical. They are already being implemented by some forward-thinking organizations. As the demand for AI applications grows, the need to continually advance these efficiency measures becomes crucial. Without sacrificing performance, we can establish systems that are both powerful and sustainable, forming a solid foundation for the future of AI. As we navigate the complexities of AI's impact on the environment, it becomes essential to examine the role of policy and regulation steering us towards sustainable AI practices. Policies are pivotal in setting standards and enforcing measures that can significantly reduce AI-related carbon footprints and promote a more environmentally conscious tech industry. Currently, various governments are taking steps to address the environmental implications of artificial intelligence. For instance, in the European Union, regulations that center around data protection and energy usage also extend to AI tech. These regulations are designed not only to safeguard privacy, but also to ensure that technology developers adhere to environmentally friendly standards. On the flip side, countries like the United States are focusing on encouraging innovation while maintaining a balance with sustainability goals. Federal agencies are increasingly supportive of research in sustainable AI and are considering establishing guidelines for energy efficiency tech development. Globally, the conversation is also moving towards implementing carbon taxes and incentives for organizations that utilize eco-friendly AI solutions. These fiscal policies are intended to push companies towards greener technologies and sustainable practices. So, what does the future hold in terms of policies for sustainable AI? Proposed measures suggest a multifaceted approach: stricter regulations on ICE energy consumption, creating mandatory energy audits for tech companies, incentives for companies adopting renewable energy sources in their infrastructure, public reporting standards mandating that companies disclose their environmental impact. New policies and regulations can catalyze significant change by encouraging technology developers and companies to prioritize sustainability. With effective legislation, the industry can align itself with global environmental goals, ensuring a harmonious relationship between AI advancement and ecological preservation. As we explore the future of sustainable AI development, it's crucial to consider how emerging trends and innovations could shape this trajectory. We must envision a path toward AI practices that respect and preserve our environment while still accommodating the rapid technological advances expected in the coming years. Predicted green AI trends, energy efficient algorithms. With increasing awareness about the carbon footprint of AI, we anticipate a surge in research and development for algorithms optimized for energy efficiency. These innovations would minimize the environmental impact while maintaining performance. Sustainable data centers. The backbone of AI, data centers, will likely see significant advancements in green technologies, incorporating renewable energy sources, enhanced cooling systems, and smarter energy management solutions will be critical. Circular economy models. The tech industry will shift towards reuse, repair, and recycling of electronic components, reducing waste and promoting sustainability. Decentralized AI. Exploring decentralized approaches such as edge computing can help localize data processing, reducing the need for large-scale data transfers and cutting down energy usage. To propel these trends, collaboration across multiple domains will be essential. Research institutions, industry leaders, and environmental organizations must come together to share insights, challenges, and breakthroughs. This cooperation will ensure sustainable practices are not only feasible but also scalable. Furthermore, investments in training systems with smaller data sets, developing tools for measuring carbon emissions of AI projects, and implementing frameworks for environmental impact assessment will play pivotal roles. By instituting these measures, we can create an AI ecosystem that prioritizes sustainability without hindering innovation. As we move forward, the goal is to strike a balance between ambitious AI advancements and our responsibility towards environmental stewardship. Fostering an environment where sustainable AI becomes the norm will not only benefit our planet, but also drive future innovations towards a more equitable and responsible direction. As we wrap up this exploration into the environmental cost of AI, it's crucial to reflect on the key points we've uncovered. We've delved into the extensive energy demands AI imposes, revealing the pressing need for energy-efficient models and practices. We examined how the sheer volume of data processed contributes substantially to environmental strain, necessitating innovative solutions for data management. The path forward is not just in technological advancements, but in collaborative efforts from all stakeholders. From developers to policymakers to end users, each has a role to play. Developers can prioritize creating AI models with improved energy efficiency and leaner data footprints. Policymakers should establish frameworks and guidelines that incentivize sustainable AI innovations and practices. End users must demand transparency and opt for services and products that are committed to sustainability. Moreover, investment in sustainable infrastructures, like renewable energy sources for powering AI technologies, will be crucial. Such initiatives not only mitigate the negative impact on the environment, but also pave the way for more accessible and equitable AI technology globally. The collective effort towards sustainable AI practices is not just an environmental imperative, but a moral one. As leaders, innovators, and citizens of this world, let us forge a future where the benefits of AI do not come at an ecological cost. Together, we have the power to shape a harmonious future where technology and nature coexist sustainably and beneficially. Join the conversation, support sustainable AI initiatives, and let's make a lasting impact for generations to come.